So we're going to look at another exercise involving the law of sines. And we're going to see that this it's a little bit more complicated than exercise 1. We have an added complication here. So in number 2, we're going to solve a triangle if we know angle alpha is 53 degrees, side A is 20 centimeters, and side B is 24 centimeters. So here we know we're given one angle and two sides, so we have to find angles beta and gamma, and we also have to find side C. We've got one side, so here we got two angles to find and one side. So I don't see a super easy way to start here because we can only use the fact that the angles add up to 180 when we know 2 out of 3. Here we only know 1. I am going to try to draw a sketch of the situation here, rough sketch. And let's see, 53 degrees at alpha, so if this is alpha, across from it is 20 centimeters is A. If this is angle beta, across from it is 24 centimeters. If this is angle gamma, across from it is side C. And, well, let's see what we can say using the law of sines. I have my little note card here with law of sines on it. You do not have to memorize this in my class. I'll give you this formula, but it's actually so straightforward it's hard not to memorize sine alpha over A plus sine beta over B plus sine gamma over C. So let's see what it tells us in this situation. I have sine of alpha is sine of 53 degrees over 20 equals sine of beta, we don't know, over side B is 24 equals sine of gamma over C. Now I want to take 2 out of those 3 fractions and try to solve. I like sine 53 degrees over 20 because those are all numbers there. Sine beta over 24 has one variable in it. I'm not too crazy about sine gamma over C right now because I have 2 variables in the same fraction, both gamma and C. So let's take sine of 53 degrees over 20 and just set that equal to sine of beta over 24. So the only unknown there is beta. I'm going to solve for beta. So I need my calculator value here for sine of 53 degrees. I get 0.7986 over 20 equals sine of beta over 24. Now this is actually a little trig equation like in the previous chapter where in order to get beta we first have to isolate sine beta. So I'm going to multiply, I'm just going to multiply both sides of this equation by 24 so that it cancels on the left. On the right, I'm going to have 24 times 0.7986 over 20 is equal to sine beta because the 24s cancel. And now let's get a decimal for that mess on the left-hand side. 24 times 0.7986 divided by 20. And now here I'm going to keep 4 decimal places because this is going to be a value of a trig function. So I want several decimal places here. 0.99583 I get when I round off is sine of beta. And now, how can I get back to beta? Well, I think the thing you should feel like doing here is taking sine inverse of 0.9583. I'm going to do that on my calculator, so I'm going to bring out the inverse trig function. Again, make sure you're in degree mode. We're working with degrees here. We don't want radian measure of angles. I'm going to enter 0.9583, and then I'm going to go backwards to an angle measure by using my inverse sine key. My calculator, I have to hit a shift. And I get 73.39 something. I'm going to round that off to 73.4 degrees. Okay. Now, here's the complication. All right. When we're trying to find beta, I'm going to write this over here. Beta can be any angle between 0 and 180 degrees, because it's the angle of a triangle. Angles in triangles are often greater than 90 degrees. They're never greater than 180. Inverse sine will always give us an angle between 0 and 90 degrees for a triangle at least. And this is related to the fact that that range of the inverse sine is negative pi over 2 to pi over 2. So here we're thinking in terms of degrees, so we're thinking negative 90 degrees to 90 degrees. But for a triangle, we're never going to get negative angle measure. So maybe just here I'm going to write a little negative 90 degrees to 90 degrees is that negative pi over 2 to pi over 2 interval for inverse sine. But because we're dealing with a triangle, we're only going to be looking at angles between 0 and 90 degrees, and that's exactly what the inverse sine gave us. But it's possible that beta could possibly be greater than 90 degrees. And so we actually have to look at another angle measure here, and I guess I want to just draw something here on the side. I'm going to go back to the unit circle. I'm not going to put a beta. I'm just going to call this angle theta. Some angle between 0 and 90 degrees. So its sine is the y-coordinate on the unit circle. It's positive, right? If I go straight across here to this point, there's another angle that's between 0 and 180 degrees that has the same sine. So what is this angle? Well, we know the reference angle is theta. So this angle that I just drew here is 180 degrees minus theta. And so what we got to consider here is we must also consider 180 degrees minus 73.4 degrees. 180 degrees minus 73.4 is 106.6 degrees. There are two possible angle values for theta, or for beta here, we're looking for beta. So beta equals 73.4 degrees, or beta is equal to 106.6 degrees. And these are both possibilities that we need to investigate. The inverse sine gives us one of those angles. The inverse sine will always give us an angle that's an acute angle between 0 and 90 degrees. A triangle, though, might have an angle that's between 90 and 180, just like we saw here, 180 minus 73.4. So the inverse sine won't tell us. We need to figure this out on our own. So this is the complication in this problem, where we actually have two possible values of beta. So the inverse sine value in 180 minus, so the inverse sine gives us one angle, 180 minus gives us the other possibility. And now we got to keep going, okay? So let me sum this up in words a little bit here. There are two possible values for beta. So there are two different triangles that meet the conditions of this problem. And so our answer gets a little bit more complicated. I like to set up a chart where I write triangle number 1, triangle number 2, and I'm going to sum up my answer in 2 columns. Now this problem started out with, we knew alpha was 53 degrees. So that's true for both possible triangles. We also knew that A was, 20 centimeters, B 24 centimeters for both possibilities. So that's the same for both answers. But what we just, again, figured out here is that there are two possible values for beta. Beta could be 73.4 degrees, or beta could be 180 minus 73.4, which is 106.6. So I just want to mention again that where these came from, that 73.4 was the inverse sine of 0.9583. So we used our calculator to get that one. The calculator is not smart enough to give us the other value. This is 180 degrees minus 73.4. We need to be able to figure that out on our own. We need to know that that step is required to find that other possible value of beta. Now, once we got alpha and beta, we can find gamma in each case, because for triangle 1, alpha plus beta plus gamma is 180, so 53 degrees plus 73.4 degrees plus gamma is 180. That tells me that gamma, if I solve for gamma here, I get 53.6 degrees. For that first possible situation. But in my second triangle, of course, the gamma is going to be different because the beta is different. So I again, I'm going to add up my three angles, 53 degrees, plus beta is now 106.6 degrees, plus gamma is 180. So that gives me a different value of gamma for triangle number 2, 20.4 degrees. And now what do we got? We got, in our answer, we got alpha, beta, gamma. We got the angles, we got sides A and B. We still need to figure out the C side for both of these. And that's going to take a little application of the law of sines in each case. So sine of gamma over C is, I can use sine alpha over A. Sine of 53.6 degrees over side C is equal to sine of 53 degrees over A, and our A was 20 centimeters. Sine of 53.6, so that's 0.8049 over C equals 0.7986 over 20, and solve for C. I'm not going to write out the steps here. I get that C is about 20.2 centimeters in that case. So for my first triangle possibility, C is about 20.2 centimeters. But then there's a second possibility where using the same fractions from the law of sines, it's going to come out different because I have to figure out what happens when I plug in 106.6 degrees for, gamma is not 106.6, that was beta. Gamma is 20.4 degrees over sine of 20.4 degrees over C equals sine of 53 degrees over 20. Make sure that stands out. Sine of 20.4 degrees, I get 0.3486 for that over C equals 0.7986 over 20. And when I solve for C here, I get C is about 8.7 centimeters, so different value for C. That I'll fill in up above. So here's a summary of my answer. Okay, we got two totally different triangles as answers to this problem that just given the information at the beginning of the problem, there were two possible triangles that fit that information. And so I want to talk about this a little bit more. And what I'm going to do is I'm going to try to pull this camera back a bit because I got something I made here to talk about a little bit. And I tried to make a model of this situation. So I made it out of paper, and I have my alpha 53 degree angle right here in the corner, and my A side 24 centimeters is right here, and then I attach to it my B side, the 20 centimeter side. Now down at the bottom is the C side. I made that real long because I don't know how long that should be. And the C in the A side, I have that angle fixed, that 53 degree angle fixed there on the side, because that's given, right? But I don't know what angle B is, so that's why I'm allowing this other side to swing. Angle beta is here. The gamma angle is here. That can also change. So this sort of has all the given information in this problem right here, and so we can kind of figure out what triangles we could get out of it. Well, how would we even get a triangle? When I swing this side up here, we don't have a triangle, right? I only get a triangle when this 20 centimeter side swings down and touches the C side. So there's one possible triangle. In fact, that's one of our triangles from the two possibilities. But now I can swing this B side down further. Now the shapes I'm getting here don't count because I have to have a 20 centimeter side. The tip of that B side has to be on the base of this triangle, the C side. So as I swing around, it's sticking out too far. But as I continue around, it swings back up again, and we reach another spot where the B side just touches, extends to the base, the C side. And this is actually the second triangle possibility. Here's one possibility for the triangle. When I swing this side over to this other position here, there's the second triangle that satisfies all the given information for that problem. And I just want to try to draw this into my answer here. This possibility is actually the one where angle B is 73.4 degrees. 73.4 degrees would be right there, 53 degrees there. Gamma is 53.6 degrees at the top. The C side is 20.2 centimeters. So in this position, this distance between my two fingers that barely fits on the screen is 20.2 centimeters. The other possible answer is represented by that position. It's a very obtuse kind of triangle. We still have 53 degrees here, but now that beta angle, there's my 106.6. Up here, this narrow angle up at the top, there's my 20.4 degree angle. And here's my C side, that's just 8.7 centimeters. So I didn't write down all the information for the answer on those two pictures, but you can kind of see there are these two possible triangles that we get from the given information in this problem. And it all hinged on that one step where the inverse sine gave us one value of beta. We had to know on our own to also consider 180 degrees minus that angle we got to get the other possible value of beta. Let me just flash the answer up here one more time, and we'll do a couple more exercises.